So that strong current really arrests that strong near inertial response. That's significant. It means that there's not a lot of mixing going on. Now, when we look at the near inertial response here in a minute to Katrina and Rita, where there was an MMS mooring out there, we'll see these packets of near inertial energy going downward in the cold core eddy as well as the warm core eddy. So here's Katrina and Rita, pre-storm. Not much of a signature of the loop current from this TMI image. And then post-Katrina, you begin to see some cooling off to the right side in this area right along that frontal boundary. We sketched this. This is the depth. This is the contour of the depth of the 26-degree isotherm. So this is where it's starting to get shallower over here. So you can see that the cooling that's where it's really taking place. And on the shelf, the West Florida shelf down here towards the Florida Straits. Likewise with Rita, again, same idea. Not a whole lot of cooling, but some cooling prior to Rita's SSTs. But again, you get about a 1 to 2 degree cooling over in this area just to the east of the storm track. So here's Rita again. Well, here's Rita. So this is the ocean heat content as Rita was coming through, and you can still see over 100 kilojoules per square centimeter available for the storm. And again, rapid intensification right in this corridor. And I would like to draw your attention to this because there was some suggestion that this warm eddy has already separated from the loop current when in fact it didn't. What happened during Katrina and Rita, we didn't go out on the aircraft during Katrina. We missed the opportunity. But then there was a lot of interest in going out and measuring what was in that eddy with a bunch of AXCTDs and AXCPs. So that's what we did, and we did this star pattern over here. And we were working with Rick Lumpkin and his drifters, and he put a bunch of drifters in the warm eddy. So there was some question whether or not this ring was separated from the loop current. You see some idea that there was some separation, but it wasn't fully separated. And that's what the altimeter was also saying. But so the thing that happened is that we went out and did this post-Katrina flight, and what happened? Well, Rita was coming through the same area. So again, I'd like to say that we planned this, but we did not. We were fortunate enough to get back on the airplane and get out there with more measurements so we could see what was going on with this cold core ring and the separation process. It turns out that altimetry during that period of time, there was some problem with one of the altimeters. And having this data allowed us to really understand what the real phase speed of this warm core ring really was. If you looked at some of the uncorrected altimetry, it said that this thing was moving 20 to 25 kilometers per day. There's no way these things move that fast. This was actually moving something on the order of 3 to 5 kilometers per day, which is much more realistic and within what many others have observed with altimetry and other measurements. So here's really the crux of the issue. So here's the warm core ring. No, not a whole lot of evidence of the cold core ring. This is on this transect going right through here. So this is this is post-Katrina, pre-Rita. And then after Rita goes through, what happens? This cold core ring comes going around the periphery. Of course, we know we need those cold core rings to help with the instability process for the eddy separation and eddy shedding. So it's another nice data set that we were very fortunate enough to get our hands on. And then we also had access, there was a couple moorings up here that MMS had put out. So we got a hold of that data in discussions with the MMS folks. So here's where the moorings were, right over in this area. as the storm moved over for both of these storms. And what we did is we just looked at the geostrophic flow field and normalized it by F to get some sort of an idea of what the relative vorticity is. You can see how the vorticity is changing, and in the Isaac, I'm going to show this much more conclusively. It turns out that the geostrophic flow fields can actually either enhance or diminish upwelling. So this mooring is shown down here, and here's where you see these packets of near inertial energy. This is away from the loop current and the warm eddy, and you can see this really nice radiation of near inertial motions going down. It's much more vivid in this. You can see, so this is the near inertial response now at that mooring, and the color bars represent temperatures, and the magnitudes are represented by this arrow up to 50 centimeters per second. So it's a beautiful indication of how those waves are just going around and getting down into the thermocline and ringing the ocean. So this is really what a lot of people thought that we didn't. So let's get back to what the original premise was, that they thought this happens everywhere all the time, but it doesn't. It happens outside of the loop current. It happens outside of the warm rings. So that's why we have to pay attention to the loop current for its heat, okay? Because this would really, strong near inertial currents like this would really cool the ocean. But as I showed earlier, the ocean wasn't significantly cooling during those two major storms. So water mass transformation. So this is Katrina with a cold core eddy and Rita with a warm core eddy. And you can, so this line is the typical TS relationship for the subtropical water coming through the Yucatan Straits. And you can see how the things were changing pre, during, and post in terms of the stronger mixing in the cold core eddy versus not a whole lot of mixing in the warm core eddy. Quite striking in TS space. So you bring the TS space in to basically corroborate what you're finding with the shear and the mixing. And this is an example of an AXCTD, and AXCTDs do work. So they work quite well. We've been deploying them for a number of years. So the summary then from Katrina and Rita was, in the loop current, we saw cooling of about 1 degree, maybe 1.5 at the most. So what are these lines? Pre is solid, during or in storm is dashed, and post is red. And you can see, yes, the mix layer deepened, but it's deepening it with, so there's deepening, but you're mixing really warm water with just warm water, so it's not going to cool. By contrast, in the shedding front, we see about 4.5 degrees C. As a shedding front, you're beginning to do a lot of upwelling and mixing going on, and you're not seeing significant cooling. So that's why we need to know where these features are. And finally, in the warm core eddy itself, same scenario, deep warm thermal layers that are already there, just like in the loop current, and we see temperature changes of about 0.5 degree to 3/4 degree. So understanding how these temperature changes then relate to the air-sea flux of heat and moisture is critical in understanding the forecast problem. Isaac. So Isaac was one of the storms that we did for GOMRI funding. This was back in 2012. And the irony was, with this storm, it was a weak tropical storm down in here, but as the storm was moving towards the northwest, it was beginning to slow down. What happens when a storm slows down? You get more upwelling. Why? Because the winds are just pushing the water away from the center of the storm. And by conservation of mass, water has to upwell. But so upwelling is a function of how fast that storm is moving. So in this case, it was moving at about 1 to 2 meters per second, much slower, kind of like Miami traffic, if you will. So this is a summary of what we did on the post-Isaac flight. Let me go. But in total, we deployed 58 AXBTs and a total of 218 ocean probes. So that includes AXCPs and AXCTDs. During about 6 flights, we had a success rate of about 88 to 90%, which isn't bad when you're throwing probes into a storm. And the different types of dots here represent either CTDs, AXBTs, and AXCPs. The reason you tend to see more AXBTs is they're free, which means they're inexpensive. I'd like to say cheap, but I'm going to say inexpensive. But a lot of these old AXBTs are from the Mount Pinatubo era, which was a long time ago. And this is the TS curve that came out of all the data. Pre-storm is black, red is in-storm, and post-storm, so you see some mixing going on here too. Now, from an atmospheric perspective, I always get these questions. Yes, but how does the ocean really relate to our measurements? Their measurements being GPS sondes. So a GPS sonde is thrown out of the airplane. It has a parachute, goes down and measures temperatures, moisture, and winds as it descends all the way down to the sea surface. So what we like to do when we do these deployments, ideally you want to do an AXCP with a GPS sonde. Why? Because you get surface winds and then you get near surface ocean currents, right? So that's really important. It gets back to that issue that I outlined earlier about drag coefficients. What is the drag coefficient in a strong wind field? No one really knows that. There's a lot of hand waving that goes on and a lot of empirical studies, but the error bars are quite large. So what is that number? So one way to do it is dropping these combos to use the ocean mixed layer currents as a tracer of momentum that's coming in from the wind field. In addition, the AXCPs also measure the surface wave induced orbital velocity. So it gives you some idea what the surface wave contribution is as well as the mean mixed layer currents. And this goes back to some of Tom Sanford's early work where he showed how valuable having these types of measurements were in the oil spill or for the oil consortia a long time ago. Now, let's get back to OHC and the eddy field. So over here, here's a warm eddy. So this is a warm, so Isaac went right between the two, intensified to Cat 1, had a fairly broad wind field, so that's what this black contour represents. And then over here is more of a cold core feature. So you can see kind of the difference that's going on. Again, you don't see much of an inertial motion in this current plot. But over here, that's what you're seeing. You're seeing a rotation of the current vector with depth. Again, it's in a cold feature compared to a warm feature. So the response differs significantly whether you're in a deep warm layer or in a thin mixed layer. Again, yet another example of what's going on underneath the storm with the current field and the importance of the momentum response. And here's sort of an idea what the water masses were for Isaac. Again, the subtropical water, the typical curve of something that looks like this that you see in the warm eddy field. Gulf common water, which is outside of the eddy field. So up in this region, we're suggesting that there was very strong upwelling and mixing, and then down in this region, there was just more upwelling. More upwelling, presumably associated with the slower moving storm. Now, one of the interesting parts to this is what Benjamin worked on, and so he was looking at comparing and contrasting these features. And one of the things that popped out of it was, I alluded to the enhanced upwelling associated with the geostrophically balanced currents. So here's the gradient of the geostrophic flow field from altimetry. okay? So the surface currents that we get out of an altimeter. Now, Stern, a long time ago, came up with an idea that this is really important in some problems when you're trying to understand upwelling. This first term, without it, is what? That's just your Ekman term, an Ekman-like term. You know, it's just the stress over the Coriolis parameter. But a second term that Stern's put in was this gradient in the geostrophic flow field. And what that did is it actually enhanced the vertical velocity. So again, this gets back to the pre-storm or environmental conditions with the flow field and its importance on the ocean response, and now not just vertical mixing, but also upwelling and downwelling processes. So, and then you can see it, you basically can see it over here with these contours showing where this enhanced upwelling occurred. And I would like to point out that this is right around the DeSoto Canyon area. And if we go back to 2010, this is also that area where Deepwater Horizon occurred. So there was a lot of interest in this data set. So upwelling is important, mixing is important, background flow fields are important because it modulates the level of the ocean response in SST cooling and ocean heat content loss. Those are, so it gets down to the momentum, the momentum response. And here's a little bit better depiction. Here we have an example of downwelling, so pre, dashed, solid, in storm, and post. So you see an awful lot of upwelling on the order of about 20 meters going on, 20 to 25 meters going on here in this region. Over in this region, you see some evidence of upwelling. Again, same connotation. Dashed for in, pre, solid for in, and red for post. So you see this contrast between these 2 points. So there's a lot of physical processes going on that's changing the upwelling and downwelling process underneath the storm itself. And that's related to what? Background stratification, background geostrophic flow fields, and of course, it's related to how fast that storm is moving. So we also did Gustav and Ike. I'm not going to go into details about that one, but the same thing. It was a interaction with a loop current. Loop current didn't significantly cool. The paper was just published in JGR this year by one of my former students. But it's the same scenario. Lots of cooling occurred up in here, away from the loop current, and not much cooling occurred in the loop current itself. So we need to know where that feature is if we're going to make a good hurricane intensity forecast. We need to know that. And we were fortunate enough to work with Bill Teague at the Naval Research Lab. He had a whole bunch of moorings out during Hurricane Ivan. This is in 2004. 14 ADCPs. Here's the DeSoto Canyon again. Storm moved right over that particular area. It was projected to go into New Orleans, but fortunately it made a last-minute detour and hit the between Mobile and Pensacola. Another beautiful data set, and this is an example of the observed currents over at one of the moorings, 1.5 radii of maximum winds to the right of the storm track. You see lots of shear going on in the upper ocean, and so this is observed. And then, of course, with the mooring data, we're able to resolve the near inertial contributions even more because you have a nice time series. So you can see where these regions of enhanced shear were. And of course, there was no warm or cold core eddy that we had to worry about here. This was like Gulf Common water. It was just a mixed layer of about 30 meters, and underneath there, just your regular background thermocline. So, what are we doing now? Well, we're still doing the expendable work, but Tom Sanford has now developed E&M Apex floats. E&M Apex floats take what he did for the AXCP and now put them into a float. So we currently have 8 of these. These are air deployable out of the WC-130s that are up in Keesler Air Force Base. So we're going to be deploying those. And what type of, so these were deployed in Josephine. That was the first test case. They were developed by Tom at Teledyne Web Research. And you can see quite nicely the nice near inertial beams going down again. Okay? It was also an area of some eddy variability, but the strong ocean response to the hurricane overwhelmed what was the background there. The background was relatively weak compared to what we see in the Gulf of Mexico. This was just north of the Antilles. So he packaged this into a nice float. It's been already proven in hurricanes. They also deployed these in the Western Pacific during ITOP. Great data set. So not only do you get U and V, you get salinity and temperature, and you can begin to do what? Calculate things like Richardson numbers and relate Richardson numbers to the wind and the stress and the fluxes. So over the years, we've combined these aircraft surveys with moorings, drifters, or ship-based measurements wherever possible. When you bring together these different measurement platforms, you begin to learn a lot, and it's very useful to understand things like heat, how much heat is being lost, what is the shear, what is the momentum balance, what's going on underneath the storm. These are important if you're going to build an ocean model that's capable of making accurate forecasts of hurricane intensity. It's something near and dear to all of our hearts because you live in the Gulf of Mexico over here. You know, we're right on the border of the Florida Current, you know, coming right out of the straits. So we want to understand this because it makes a difference for getting people out of harm's way. So it has a lot of societal relevance. So negative feedback regimes, cooling, mixing, large SST decreases, large OHC decreases, and you get the negative feedback, which means the air-sea fluxes aren't nearly as dominant, or the air-sea fluxes feeding the storm aren't really exciting the storm beyond a certain threshold. Positive feedback over loop currents, warm rings. It happens in the Western Pacific as well, over in that area around the Kuroshio and that eddy rich field just east of the Kuroshio. We're seeing this in a lot of different places now. So the forecasting models really have to begin to ingest good ocean data. SST is modulated by these features, and they do have an impact on the air-sea fluxes. That's been shown repeatedly in several papers that we've published, as well as papers that were published in the Western Pacific. Targeted observations are important. If you're going to go out there and take these big P3s and just get, you